I think let me just quickly welcome all the people on the bridge for this Accion weekly knowledge sharing series. Looking forward for today's session. We are going to talk about machine learning presented by our CTO Ashutosh Bijor from Mumbai office. So looking forward to an exciting demo today. Let's get started. Okay, over to you, Ash.
Thanks, Anup. Okay, this is a very high-level introduction to machine learning. This is not a technology session. This is more from a perspective of understanding what is machine learning. And I'll give a few resources at the end for people who are interested in learning more about machine learning. So, a few months back, there was an article in the Wall Street Journal where it says that in retail, data elbows aside chief merchants. Now, what this means is that, let me first explain the context. In the retail industry, the most important thing that drives their business is the decision of which products are to be distributed and sold in which location. For example, in different malls and different locations, there are different kind of products which are stocked, and the retail company typically has a person called the chief merchant who has a lot of experience in spotting trends of which products will sell and which products will not sell, and based on this experience, they make some decisions based on what their understanding is, a little bit of data that they collect from the market. They make these decisions. Now, in the recent times, what has happened is these chief merchants' intuition is not really working as well, and instead of relying on these chief merchants, retail companies are now looking at technology and specifically big data to remove the guesswork out of the manual process of deciding which products are going to sell and replacing it with that. Now, this fact is not really surprising, but we need to understand why this works in the first place. And this really represents a major change in the approach in which we used to do analytics before and the way we are doing analytics now. So let us look at what's the difference between old style analytics and new style analytics presented by machine. So conventional business analytics works in this very simplistic flow chart. So it starts with a report like the merchant we talked about in the retail. He, based on his experience and his knowledge, he makes certain hypotheses. Now the hypothesis is expressed in the form of some sort of a rule, for example saying, if last 3 years a particular product keeps increasing in sales, then in the next year you increase the amount of stock of that product by 20%. Okay, so this is a form of a rule, and it is in the form of a hypothesis which says if the product is trending to increase in consumption, then you increase the stock. If it is not increasing in trend, then you decrease the stock. So that's like a hypothesis. And you define the metrics. The metrics are saying for this particular rule or hypothesis, you need to measure the volume of sale, okay, for which you will first collect data from the field, and then you'll extract the volume of sale for those specific products. And then you'll validate whether the trend is positive or it's negative. And if it is positive, you'll make one decision. If it is negative, you'll make another decision. This is a very simplistic way in which I'm describing, but the most important thing here is that the entire process of business intelligence is geared towards validating hypotheses that were made and hypotheses or rules that were made by human experts. And so the entire process of conventional business intelligence is tuned to try and address the requirements of the analyst.
May I request everyone to mute their phone so that we don't have any background noise, please?
Yeah, thank you. Okay.
Please go ahead, Ash.
Yeah, so this is the way conventional business analytics intelligence works. So the expert makes a hypothesis or a rule, and then we collect data from various sources to try and validate that hypothesis. Now, in the new model of business intelligence, you don't need a human being at all. Basically, what you do is you collect data from the field. And now this data, you remember, is in all different formats. So for example, let's take a simple example. Data that is of actual products sold at the mall is captured at the payment counter in the point of sale system. And this point of sale data contains all kinds of noise and, for example, the description of the product may be different at different malls. The product code sometimes is not the same. We are actually working on exactly this kind of an application for one of our customers now, where they collect data from point of sale systems, and then they try to track which products are actually sold at various locations. Now, this data has raw data itself. In the conventional way, what used to happen was you collect this data and then you try to map it to specific product volume. Now, in the machine learning model, what happens is you don't try to build any hypothesis saying that the trend is what determines the actual volume of sale for a particular product. The algorithm actually collects all this data and then automatically finds patterns of whether products are increasing, which products are increasing, what are the different attributes that determine, is it the, attributes of the product, is it the location, is it the month, is it the, time of the year, whatever, right? There are so many different attributes that can determine the sale of a particular product. Instead of depending on a human being to make these rules, what the system does is it actually looks at the pattern, actual raw data coming in, and then you can derive insights out of it. Now this seems like impossibility. How can a machine actually find out these rules or these patterns on its own without a human being trying to make sense out of it? Let's look at the big difference between conventional business intelligence and digital business intelligence or machine intelligence. Firstly, conventional business intelligence is based on manually defined rules, like we just saw in the retail example. And the machine learning, they are self-learning algorithms which automatically derive patterns from the data. Now, the most important difference is that to be able to derive patterns, you need a large volume of data. Because if you just have a few samples, of data which is coming from the field, the patterns are obviously having a lot of error margin, and therefore those patterns may not necessarily make sense. So if you are able to collect all the data from all the different locations, which was earlier not possible at all, then these algorithms will start making sense. So the new business intelligence expects that you are collecting a large volume of data, and you are collecting raw data with all the different attributes rather than collecting only specific attributes. In the conventional business intelligence, what you do is you collect the raw data and then you ETL, extract, transform, and load that data into a data warehouse based on the metrics that were defined by the business analyst. So you're not analyzing all the different data, you're actually deriving specific attributes from the data in conventional business intelligence. While in machine learning, you're actually deriving patterns from all the different attributes of the raw data itself. The next is that because conventional models are based on rules, rules are typically very simplistic or very purpose-specific models. Like the example I gave you where you're saying, find the trend of volume of products sold. You can make other hypotheses such as dependency between, let's say, customer segment and product sold. Now, all of these each hypothesis has certain metrics or the variables based on which the rule is defined. And then you need to create different model for each of those hypotheses or rules. So in conventional business intelligence, you need to make several different models for each of the different hypotheses, and then you have a very complex, decision process of figuring out, like a decision tree, saying that if this hypothesis, then if the second hypothesis, then if the third hypothesis, and so on. So there are very, very complex models that are required in conventional business intelligence. In the new model, because human beings are not making any of these rules, you are analyzing all the different data at one go in one multi-purpose model. Now, this is possible because you are not trying to create rules manually. These patterns are derived automatically, and we'll understand this specific information in a little more detail when we go into the learning models. The next difference is, of course, accuracy of data. The accuracy of business intelligence in conventional business intelligence is quite limited because it depends on manual hypothesis. While in the machine learning, what happens is the accuracy of the results keeps improving over time. As you process more and more data through the algorithms, the accuracy keeps improving. And that's because the algorithm is actually learning from the data. The most important difference, and that's what we see between conventional business intelligence and machine learning, is the fact that the algorithm knows how to learn from the data that it is analyzing. This is the most important difference. So we should actually first understand how learning works in the first place. So learning works in, these are the three most important types of learning methodologies implemented in machine learning. Ironically, these learning methodologies are derived from how human beings learn. It may seem ironic that we are actually looking at how human beings learn, and we are replacing human beings with machine learning algorithms. But let's actually look at how. Yeah, thank you. Okay, so let's look at how learning works. And like I said, we'll look at how human beings learn. Now, let's start with an example of how children learn. So let's take an example. How do we teach children how to recognize, say, animals, right? Do we teach them by actually defining all the rules by saying, say, okay, if an animal has 4 legs and it has got black and white stripes and it's got pointy ears, then it's a zebra. And then if the animal has got stripes, but if it is short legs and a big face, then it's a tiger. We don't teach children by making rules like this, right? How we teach them is actually by showing them pictures. So what we do is we show them pictures of a zebra, okay, and say, this is a zebra. And the child looks at the picture and tries to remember, oh, this is how a zebra looks. And you show them another picture of a zebra, maybe from a different angle, and then you say, this is also a zebra. And what the child's brain is doing is, without actually defining the rules, it tries to remember the patterns of how the animal looks. So next time, let's say you've shown the child 3 pictures of a zebra and then you show a picture of a tiger. The child may actually mistake the tiger for a zebra because so far it has never seen a tiger before. And so it may call the tiger a zebra. Then you say, no, hang on. This is not a zebra. This is a tiger. Okay, fine. I don't see the difference. And then you say, you show more pictures of tiger and more pictures of zebra. And over time, the child recognizes to find the difference between a tiger and a zebra, in spite of the fact that both are striped animals. So this is called assisted learning or supervised learning, where there is somebody who actually labels the different pieces of data that you show the learner. And what you do is you train so there is a training process where you pre-process various pieces of data by labeling those pieces of data and saying, this is a zebra, this is a tiger, this is a zebra, this is a tiger. And then you train the learner showing these sample data, and then the patterns are derived from these patterns or from the sample data itself. This model of learning is called assisted or supervised learning. The second model of learning is called unsupervised learning. Now, unsupervised learning is also used by humans. So what you do is, for example, how do we recognize, let's say, if somebody talks with an accent, we know how to make out from where that person comes, right? So we can make out a South Indian accent from a North Indian accent, from a Gujarati accent, and Maharashtrian accent, and each different state or different language origin has a particular way of speaking English, and we can, in spite of the fact that the person is speaking English, we can almost make out what the native language would be based on the accent that they speak. Now, how do we do this? We do this by actually finding, so it's not that somebody has told us that this one is North Indian accent and this one is South Indian accent or whatever. Nobody actually trains us, right? What we do is, over time, we find similarities between the way different people talk. And then we derive these patterns saying, hey, you know what? I've noticed that all the South Indian people talk in a certain way, okay? Some words in a certain way. And then we make those groupings based on all the experience that we have. So this is called unsupervised learning, where the learner actually creates groups of data elements based on similarities between them. And this is called unsupervised learning. The third model of learning is reinforcement learning. Now, reinforcement learning is what we call as trial and error. So what happens is, you let the learner try and say, okay, do you think this is right or wrong? This is good or bad? And the learner will say, this is good. And you say, no. You correct the learner and say, this is not the right way. This is not the right decision, or this is not the right analysis. And then the learner remembers based on the reinforcement that you give to say, is this right or is this wrong? So, the reason we take examinations, for example, is for reinforcement learning, because based on whatever you read, once you take an exam, you actually validate what you understood, whether it was right or wrong. And based on, your unit tests and your terminal examinations and so on, you finally start getting a clearer understanding of exactly what are the concepts and what is the meaning of various things that you have learned. This is called reinforcement learning. Now, each of these models, if you see, is based on various pieces of data, and these data elements are then processed by the learner. Now, in this case, it is a learner algorithm instead of a human being, but the process of learning works exactly the same. So, effectively, what happens is that the algorithm actually uses various kinds of statistical models to find patterns. Now these algorithms, by the way, are not new. They've been used for decades old. As early as in the 50s, 1950s, artificial intelligence and statistical algorithms were derived. But the reason they never worked so far was because it never had sufficient amount of data to be able to make sense and to really work reliably. So what has happened now is two major things. One is that the amount of data we are able to pass through these algorithms has increased drastically. As you can imagine, the explosion of data in mobile devices and Internet of Things and so on. There is so much data available now from the field that you're now able to make some more meaningful decisions based on these learning algorithms. It just, without a sufficient amount of data, the learner will never be able to make sense. It's just like a child will never learn, if you go to a completely new country, for example, we don't know how to even recognize what people are speaking based on their accent because it's so different from something that we have been used to. So that's the main problem of learning algorithms, that if you don't have enough data, then the algorithm is just not going to work. Okay. The second thing that has helped machine learning is the speed at which we are able to process data. So not only is the amount of data important, but the rate at which we are able to process this data also is extremely important. And so the technologies that we use now for machine learning are based on not only a large volume of data, but the speed at which you are able to process data. And so in the last decade or so, there has been an explosion of data, and big data has become a big hype. But so far it was very difficult to actually process this large volume of data. I'm sure people have heard of Hadoop and MapReduce kind of models, which distribute the processing across a cluster of large number of computers, and you are able to process the large volume of data. But anybody who's used Hadoop and MapReduce knows that MapReduce is not fast. It takes time. So for you to be able to process a machine learning algorithm, and machine learning works very similar to how a brain works in the form of neural networks. So you have a network of large number of small decision points which are based on statistical models, and it keeps learning about which of these neurons need to fire based on the incoming data, and then based on that the algorithm works. So I'm not going to really go into the details of how neural networks works, but suffice to say that the only reason why these algorithms work is because of the speed at which we are able to process data in multiple, in a huge cluster of computers. And what has now changed, and the reason why, so distributed computing existed for about a decade or more in the form of Hadoop and big data technologies. But what has now changed in the last few years is in-memory processing and in-stream processing. People must have heard of Spark. Spark is the open source model of how you can process data in a distributed set of computers by using in-memory operations rather than disk operations. So Hadoop used to work on a distributed file system, so that even though you're distributing the algorithm across multiple computers, each of those nodes had to read and write from the disk when MapReduce works. But in Spark, it works by actually having all the data in memory. It doesn't depend on the disk, and that is what speeds up the processing of data in Spark as compared to MapReduce. So with the advent of these new in-memory processing models, distributed processing models, machine learning has become now far more practical for applications to use. So again, the idea is not to understand how it works, but what can we do with it. So what is the kind of learning applications and what kind of applications can we use with machine learning? The four main type of applications that we can use are classification, regression, clustering, and rule extraction. So for example, classification is where you are able to assign a label to a piece of data. For example, credit card fraud checks or email spam or sentiment analysis of a Twitter feed, let's say. All of these are classification kind of applications. The second is regression, where you try to fit a pattern to a large volume of data. So for example, predicting the price of a product or a stock or a share, or finding the consumption level of products or services, or probability of the churn of customers. These are the kind of analysis that you can do with regression. The third is clustering. Clustering is where you divide data into groups based on similarity. And the fourth is rule extraction, where you try to derive the relationship between different attributes of data. So you find dependencies between attributes, let's say geography and volume of sale, for example, of products. So that is rule extraction. So these are the four main types of analysis that you can do with machine learning. And using these, you can actually derive a large number of analytical patterns based on these four. Now let's look at some real life examples. So the first is the most commonly, and which we use day in and day out, is what we use in search, for example. Context search. When you go to Google, you get ads which are context sensitive to what you have searched, and this is the most important innovation that Google did very early in time. And what it does is it finds the pattern between different attributes that are derived from the pages that match a particular search algorithm, and then based on that there's an algorithm which actually automatically maps various ads to the search patterns. Same way, there is sentiment analysis, which is when you have, let's say, a large volume of conversations, maybe in Twitter or in Facebook messages or whatever it is, or even say SMS messages or emails, you can actually derive whether the conversation is positive sentiment or negative sentiment, and if there is some negative sentiment going on, you can actually highlight what are the subjects that are being talked about in a negative conversation, and then take some corrective action based on that. So that is sentiment analysis. The second very interesting application is adaptive user interfaces. Now, for example, user interface design is a manual process today, which is based on certain patterns that UX experts, based on their experience, they say, what works and what doesn't work. And then they, just like a conventional business analyst, they do some tests to validate, you have this A/B tests, right? Whether a button should be of this color or that color. Those kind of rules are manually created rules for user interfaces. A new model of user interfaces are going to be adaptive, where the machine actually learns what different users, when you have applications which are used by millions of users, you can actually find patterns of which users are using which kind of features in the application, and based on that, the user interface can automatically modify itself. That is called adaptive user interfaces. The third is actual project that we are doing right now is analysis of point of sale data. I talked about this at the beginning of this talk. That is an application of machine learning as well. The fourth is self-scaling infrastructure. Now, on the cloud, for example, you are able to measure, you are able to scale up an application by automatically creating new application server instances on the cloud. Now imagine this is a reactive process. So basically what happens is if there is too much load of a particular application and you start seeing that you create these rules, right, saying that if the data volume goes beyond a certain if the number of concurrent connections goes beyond a certain limit, then you add one more application instance. Now these are again man-made rules. So you create rules of how the infrastructure should scale. Once, say, the memory goes beyond 80% utilization, spin up a new instance. If the number of database connections increase beyond a certain limit, then increase the database instances and so on. These are again manually created rules. You can actually derive these patterns automatically from the logs of applications of what. So you can predict, for example, if the number of say logins increases, for all you know, automatically we can predict that the load is going to increase. Now this is a manually created rule, but imagine if you can use machine learning to automatically scale infrastructure preemptively before the load hits the application. So that is the fourth example. Now all of these are applications that we can do right now with the kind of technology that exists. And so a few examples of where you can learn more about machine learning and the concepts behind. These are the 4 links. The first one is very easy to learn a tutorial on neural networks and deep learning. It explains how deep learning works in a very simple way. The second is Google's DeepMind, you may have heard of, that is based on the technology called TensorFlow, which is an open source platform released by Google. The third one is the what I was talking about earlier, which is a distributed in-memory processing engine, which is Spark. And Spark has a machine learning library called Spark ML, and these are the links. This is where you can begin to learn a little more about machine learning, and I guess that's all we have time for today. So Anup, can we get some questions maybe?
Yeah, so I had already requested people to post some of the questions on the text window.
Okay.
So the question from Jane is that what is the preferred tech stack for machine learning and all this AI related projects? Throw some light on the tech stack. That would be great.
Yeah. What is the preferred tech stack? So, actually there is no preferred tech stack, but the one that is open source and Apache project is Spark, and a good, based on at least from what I have noticed so far, Spark and Spark machine learning seems to be the most widespread use. Of course, each of the cloud providers has a machine learning service. Google has a machine learning service on their cloud. Amazon has got, Azure has got, every cloud provider has got a machine learning service. And that's actually the easiest to use because you don't have to build any of the code. You just have to pass the data to it, and it will do predictive analytics on its own. The catch, of course, is that you are tied to the cloud provider, and your application won't work, and the data has to be uploaded to that particular cloud service provider, and therefore not everyone is happy to use those technologies. Spark, on the other hand, can be used on your own data, on your own clusters, and therefore the adoption of Spark is much more than any of the cloud service providers' machine learning applications.
Okay. Another question from, yeah, that answers the question.
Oh, hang on.
So
Gopal has a question before that. Image recognition will also come under yes, image recognition was one of the early applications of machine learning because it is based on pattern recognition. But remember, image recognition is not necessarily processing large number of images. That's the new application. When we talk about image recognition, patterns derived on rules. For example, optical character OCR, right? Where Gopal is actually leading a project on OCR, where we are using a library, called Tesseract. Now, remember, Tesseract has pre-built rules on how characters are shaped. So it's not based on machine learning; it's based on a different algorithm. So that kind of image recognition is not really machine learning. Machine learning is where you process, you don't make any rules. It automatically recognizes whether, what the characters are. And a better application example of pattern recognition is actually natural language processing. So Siri, you've heard of Siri. There's a new version of Siri, which now the original developers of Siri have released a new version, which is far more powerful and much more rich in terms of its ability to recognize natural language. And that is a better example of machine learning than merely image recognition.
Okay.
So OpenCV is not machine learning. OpenCV is the conventional pattern recognition using rules. So that is not machine learning. Shahid has asked, is there any relationship between machine learning and grid computing? Yes, there is, because like I said, it is where you are able to create large number of instances which are connected and make it work. But Spark per se doesn't necessarily depend on grid computing. Therefore, Spark is something that you can set up almost on your own. You can create a Spark instance on your laptop and you can actually run Spark algorithms. And the same algorithm then can be rolled out to thousands and thousands of nodes in the cluster. And Spark takes care of that distribution. So you don't necessarily need grid computing to be able to run Spark. Anoop, is machine learning different from predictive? Predictive analytics is an application of machine learning. So yes, it is related. It's not different. It's an application of machine learning. Can email spam filter come under machine learning? Yes. The new type of email spam filters are actually based on machine learning. So Google's spam filter, which is embedded into Gmail, based on machine learning. But some of the old spam filters used to depend on rules. Now example, quick heal kind of application, virus application. They are all based on somebody actually recognizing and doing a lot of work in defining the patterns of how a particular virus looks like, and those signatures are manually created by someone to be able to for the application to recognize what is a virus and what is not. So those are rule-based systems, but the spam filter kind of applications, especially the ones which are embedded in Google, are based on machine learning. Okay, any other questions? Otherwise, I think we already spent 10 minutes over.
Hey Ash, this is Tony. I have a quick question just on the sales front. Do we have any collateral, anything at all that we can send? And specifically, do we have some history in helping clients on Spark? So it's a two-part question. Do we have anything we can send out? And a third part of it is every client potentially a target? Would every client use Spark, or only clients with certain big data or whatever the amount? How would? So that's a three-part question.
Okay, so first, Spark is too new, and so we don't really have too much of prior project experience. We are now working on a couple of projects. Change Healthcare is using Spark. MSA is using Spark. Though we have not started using Spark in MSA as yet. MSA itself is using Spark. Yes, there are a few ongoing projects where we will be or are using Spark, but it's not yet. They are not yet complete. Some of them are POCs. So it's a bit too early for us to actually make collateral which is based on actual experience.
Okay.
I think the collateral is going to be more like what we can do rather than what we have done.
Okay.
And part of the new website, we are actually planning to put some of the content around Spark about what we can do with Spark. That's the first question. I think first two questions of yours, Tony. The third question was, sorry, you said who can use, right? That's a great question actually, because theoretically everybody can use. Any kind of conventional business analysis which is based on data collection and validation of hypothesis can technically be converted into Spark and machine learning. But the big condition where Spark actually works is when the volume of data or the complexity of data is very, very high. So if you have simpler type of data and there are existing business rules which are created, typically let's take say company performance, right? Performance analysis of accounts of a company. Now already the data is very structured in accounts, right? You're not trying to figure out how money was made. You actually measure the volume of money that is made in an accounting system, and then analysis is based on that data itself. That does not make any sense to use Spark for. So those kind of conventional rule-based systems where you have structured data are not really suitable for Spark. When you go out into the world where there are more customer-facing applications, CRM, support, social media, anything that is customer-facing where you have large number of people having unstructured, and what we mean by unstructured is basically human conversations, machine-generated data, anything that is not forming in the core of the application, enterprise, where automation of conventional business processes was based upon those, very well-defined rules. So those kind of applications may not really be easy to transform into the new model, but as we go outward from the core of the organization, it's going to become more and more difficult for conventional technology to handle that kind of volume of data, and that's where the new algorithms are going to work and Spark is going to work.
Okay. Cool, man. We had one account about a month ago. I'm going to reach back to the guy. He was looking for a Spark internalist, someone who could actually build the product, not someone who has used it. Of course, it was really challenging. We couldn't come up with anybody. Yeah. But if you had 1 minute with this guy, what would you, how would you? Or if I reach out to him and say, hey, man, we want to talk to you, what 2 or 3 things would I want to point out to him?
Well, Tony, frankly, for anybody who looks for an architect who's just going to design, it's going to be a little difficult for us to do that. We don't have anybody who's got years of experience in Spark, and we don't have people. We are not in the consulting business, I guess. So when we have consulting type of roles, I think it's going to be really difficult for us to address those. I think a better bet for us is enterprises who don't know Spark, and we can go and help them implement some simple applications in Spark. So anybody who's expecting a deep expertise of Spark, I don't think we'll be able to address at this point.
Okay. Fair enough.
It's premature for us to do that.
Okie doke.
Okay, so that's a great knowledge sharing session today. Ash, thanks to you. And for people who are on the bridge, if you have any questions, please do share those questions with me, and I will consolidate that and share it with Ashutosh so that we can expect a response on that. I know that there are some more questions.
Anup, I have shared
one more question.
Yeah,
sure.
So I think the real-time ads which appear on any of the browsing site or websites, that is also a part of ML.
Yeah, that's the example I gave Gopal earlier of context-sensitive ads on Google. That is that certainly does use.
Right. So I think we definitely can conclude this session. Ash, Kinesh, would you like to add any closure notes as what you usually do in there?
That's
Kinesh,
okay.
you there? Yeah, no problem. So I think we had a full house today. All the 25 slots were taken. Thanks for everyone for participation in this knowledge sharing session, and we look forward to catch up with another interesting demo in a fortnight's time. Looking forward to connect with you all again in 15 days.
Thanks, Snoop. Thanks, Ash. See you, everybody.
Bye.
Bye.